In part 1 of this series of programs, you learned that sensors play a crucial role in the operation of a vehicle. Thus, if a sensor should fail, this could cause serious system malfunctions. Here's a case study to demonstrate this point. A passenger car that has been parked outside overnight in the cold will not start. On site, the service 24 hours employee first checks the battery voltage, the tank fill level, and the start enable function. No fault can be found, however. There is also no fault code stored in the fault memories when they are read out by the diagnostic system. The vehicle is then taken to the workshop, where it is left inside for several hours. When the service employee tries to start it again, the engine starts without any problem. What might be causing the starting problems on this customer vehicle? Further troubleshooting reveals that the sensor signal of the crankshaft position sensor differs from its correct pattern. In certain ambient conditions, it's possible that the signal will be below the response threshold of the engine control module. This case study demonstrates that in certain situations, reading out the fault memory is not enough to detect a fault. In these situations, it is useful to have an understanding of sensors and their signal forms. This will be covered in the following section. This chapter deals with the signal forms of sensors. First of all, you will learn about the various types of output signals and how these can be recognized using the signal form. The next section explains the function of response thresholds in control modules. Electromagnetic interference can distort sensor signals. How this can be prevented will also be dealt with in this chapter. Finally, you will discover why many sensor signals have to be converted and digitized first before the control modules can process them. Sensors have different types of output signals. Some sensors, such as oxygen sensors, generate a voltage signal. The wiring diagram shows the arrangement of the voltmeter probes for measuring the sensor voltage. With a rich mixture, the sensor generates a voltage of around 850 millivolts. With a lean mixture, the voltage is around 150 millivolts. Other sensors, such as photo elements, for example, generate a current signal at their output. The current intensity is used by the control module as a measure for the physical variable. In the case of photo elements, this is the luminous intensity. To measure the current, the electric circuit has to be interrupted at one point to connect the ammeter. The photo element current now flows through the ammeter and can be measured. As you do so, observe the deflection of the pointer on the ammeter. When luminous intensity is low, the output currents from the photo element to the control module are low. When luminous intensity is high, the photo element generates a high output current. Another signal variable which can be analyzed by the control module is ohmic resistance. An example of this are the NTC resistors which are used in the vehicle for measuring the temperature. However, the control module cannot measure the respective resistance directly. Instead, it calculates the resistance from the intensity of current flowing through the resistor and the voltage applied. In a similar way, the resistance can also be measured separately with the ohm meter. This is done by splicing the lines on both sides or removing the NTC resistor. A measuring current, fed by the battery voltage of the ohm meter, now flows through the NTC resistor. At low temperatures, the resistance is high. At high temperatures, the resistance drops. Some sensor signals may have to be converted into a suitable signal form before the control module can process them. One example of this is the hot film air mass sensor. It determines the mass of air drawn in by the engine. This is done by an NTC resistor, which measures the cooling of a heating resistor located in the airflow. An electronic regulator keeps the temperature rise on the heating resistor constant. It thus converts the resistance of the NTC resistor into a current signal of the heating resistor. In a second stage, the sensor's electronic analysis system converts the current signal at a current sensing resistor into an output voltage which the control module uses as a measure for the mass of air being drawn in. Many vehicle sensors generate output signals with regular or irregular oscillations. Here, the physical variable is expressed by the frequency or the amplitude of the oscillations. In the case of inductive wheel rotational sensors, for example, the amplitude and frequency of the oscillations are dependent on the speed at which the toothed segments move past the sensor. This, in turn, is determined by the vehicle speed. Have a closer look at the signal form of the wheel rotational speed sensors. As you do so, observe the signal in the oscilloscope. See how the frequency and amplitude of the wheel rotational speed sensor signal increase as the vehicle speed increases. The control module calculates the speed in kilometers per hour from the frequency and displays this in the instrument cluster. Some sensors can also generate square wave pulses. One example is the camshaft Hall effect sensor. As soon as the toothed segment located on the camshaft passes the sensor, the Hall voltage generated by the Hall element increases. The sensor's electronic analysis system processes the signal and converts it into a square wave signal. The electronic analysis system transforms the pulses of the toothed segment into so-called low states and the gaps into so-called high states. This signal is sent to the control module where it is evaluated. Sensors often only generate low voltages or currents. For example, at low engine speeds, the crankshaft position sensor generates a signal with only a low output voltage. So what's the signal of the crankshaft position sensor like when the engine is not running? Even when the engine is not running, there are still low oscillation signals on the control module. These are caused by electromagnetic interference signals. To ensure that the control module does not mistakenly evaluate these signals as sensor signals, control modules have a response threshold. A measurement will only be registered and evaluated in the control module when a signal exceeds this response threshold. En route from the location of the sensor to the control module, it is possible for sensor signals to be drowned out by interference signals. Here you can see such an overlay using a sinusoidal sensor signal by way of an example. The sensor signal and the interference signal combine to form one common signal. On the next few pages, you will see what measures can be taken to counteract the effects of interference. One simple procedure to reduce electromagnetic interference is to amplify the sensor signals in the sensor. Here's the example of the sinusoidal sensor signal, which you are already familiar with from the previous page. By amplifying the useful signal in the sensor, the interference signals have a proportionally lesser effect than they do on non-amplified signals. As a result, the control module can evaluate the signal more effectively. Another way of protecting the signal lines from electromagnetic interference is to twist the lines. In this way, the interference voltages affecting the lines will cancel each other out. Another method is to shield the lines with a metal mesh which is connected to earth. The interference voltages acting from the outside will be absorbed and diverted by the metal braid. Most sensor signals are analog, which means they are continually varying electrical variables. However, the control module processors in vehicles are digital. As a result, analog signals must first be digitized. This analog-digital conversion is performed either in the sensor itself or in the control module's input circuits. In the simplest form of digitization, the analog signal is converted into corresponding square wave pulses which switch between high and low states. One or several response thresholds determine when to switch from high to low and from low to high. As soon as the analog signal exceeds the selected response threshold voltage, a high signal will be generated. For example, if, on the other hand, the analog voltage drops below the threshold value, a low signal is generated accordingly. The threshold voltage setting depends, amongst other factors, on the analog signal to be evaluated and the desired measuring range. Here you can see a simple digitization of an analog wheel rotational speed signal when braking. The inductive wheel rotational speed sensors output an analog signal whose frequency and amplitude continually decrease as the vehicle's speed decreases. As soon as the vehicle comes to a stop, the inductive wheel rotational speed sensors stop sending signals to the control module. To convert the analog signal into a digital signal, a response threshold must be set. If possible, this should be set in such a way that enables the control module to detect vehicle movement right up until the vehicle comes to a stop. In order to be able to detect vehicle movement right up until the vehicle comes to a stop, the response threshold must be set so that even the smallest oscillations can be processed by the control module. This will be achieved if the response threshold is in the center of the signal. What happens if the analog wheel rotational speed signal is overlaid with an interference voltage? Let's have a closer look at a section of the signal. The enlarged section shows that the signal rises above the response threshold repeatedly in two places. Have a look at the corresponding digital signal as well. At the points where the interference voltage causes the analog signal to briefly exceed the response threshold, additional digital pulses are generated. These will corrupt the information sent. To prevent this from happening, two response thresholds are used. A switch from low to high occurs when the signal exceeds the upper response threshold. A switch from high to low occurs when the signal drops below the lower response threshold. This ensures that interference signals which fluctuate between the two response thresholds are not evaluated. Some sensors, such as oil sensors, generate a pulse width modulated signal, another form of digital signal. Here, the measurement information from the sensor is contained in the width of the square wave pulses. In the case of the oil sensor, the temperature, fill level, and quality of the engine oil is transmitted in turn to the control module. The pulses are repeated at regular intervals. Digitally encoded signals ensure a more precise measurement reading. Here, the analog signal curve is sampled at regular intervals. Each individual measurement is represented by a digital data block. This process is used, for example, for the steer angle sensor on trucks with intelligent stability control. In some cases, the signal is already digitized in the sensor. This has the advantage that the sensor signal is not affected by electromagnetic interference on the signal line. Provided the interference signals do not cause a switch from a high signal to a low signal, or vice versa, from a low signal to a high signal, then they will not alter this sequence and the information being transmitted will not be affected. Let's summarize the chapter again. Sensors generate different types of output signals, such as voltage, current, ohmic resistance, regular or irregular oscillations, and square wave pulses. Control modules have a response threshold. This ensures that a signal is not registered by the control module until the signal exceeds a certain level. Electromagnetic interference can seriously corrupt a measurement. One simple way of reducing these interference signals is to amplify the sensor signal. Twisting the lines or shielding with an earthed metal braid can provide additional protection. Sensor signals must be digitized before they can be processed further in the control module. This can be done either in the sensor itself or in the control module. Digital signals are insensitive to interference signals. This chapter deals with the calibration of sensors. We will first examine what is meant by the terms statistical and systematic errors. The next section deals with the calibration of sensors and explains in what circumstances a calibration is required. Finally, using various examples, you will learn about who can perform a calibration. If you measure the same factor, for example temperature, several times with the same sensor, the sensor will produce slightly different measurements each time. These will sometimes be above and sometimes below the true measurement. These deviations are known as the statistical error. Thus, in principle, there is always a degree of inaccuracy in measurements. However, most of the measurements will be within a tolerance range. For example, temperature sensors usually measure temperature to within an accuracy of plus or minus 1 degree centigrade. It makes no sense, therefore, to indicate measurements with more decimal places than the measuring accuracy of the sensor. It is also possible that the individual measurements will tend to deviate from the true measurement in one particular direction. This adds an additional systematic error. This indicates that the mean value of the measurements will deviate from the true measurement. The systematic deviation remains constant for each sensor, but differs from sensor to sensor. The sensor manufacturer provides a characteristic curve with a tolerance range for the type of sensor. In this case, an NTC resistor. The tolerance range indicates that most of the measurement results from sensors of this type will be within this tolerance range, despite the statistical and systematic error. This spread of measurement results causes different vehicles to have different responses. Let's take a look at an example. All control modules of a specific vehicle model detect overheating when the coolant temperature reaches 120 degrees or above, and respond by limiting the engine's power output. In terms of the true measurement of 120 degrees centigrade, one vehicle could report overheating at 119 degrees centigrade because this particular sensor has a systematic error that is 1 degree higher than the true measurement. On another vehicle, however, engine power output may not be limited until the temperature reaches 121 degrees centigrade, as the sensor has a systematic error that is 1 degree lower than the true measurement. Provided this type of scatter range caused by the statistical errors is acceptable, there is no need to replace a sensor. If a sensor's systematic deviations are not acceptable, it must be replaced or calibrated, depending on the system. If, for example, the measurements of a throttle valve potentiometer are continually above the true measurement, it would be worth calibrating the system to assign it a shifted characteristic sensor curve in which the systematic error is incorporated. Calibration can be done during vehicle production, during a service, or automatically by the system concerned. Here's an example of a calibration being performed during a service. To calibrate the steer angle sensor of the M-class, the vehicle is driven in a straight line for a precisely defined distance. During this process, the control module learns to recognize the measurements from the steer angle sensor as being the steering's center position. This information is stored in the control module and is used as a reference value for any subsequent steering maneuvers. The driver can also carry out a calibration. For example, the driver activates the tire pressure monitoring system if he has changed the tires, for example. The calibration enables the new tire pressures to be accepted as the set values. Some systems carry out calibrations automatically. One example is the clutch system on an automated manual transmission. Here, the clutch travel sensor on the central release lever registers the position of the clutch release bearing. To optimize clutch engagement, the grip point and the clutch engagement point are continually recalibrated by the control module when starting the engine and after every gear change. If this did not happen, the clutch might slip or grind. Like with the center steering position calibration, it's not just the sensor, but the entire system that is calibrated. In these cases, any systematic sensor errors will not cause a malfunction, because the system is constantly calibrated to the sensor's measuring inaccuracies and therefore takes account of them. Let's summarize the chapter. When recording variables with a sensor, the measurement results will always randomly deviate slightly from the true measurement. This principal measuring inaccuracy is referred to as a statistical error. If the measurement results also deviate regularly from the true measurement, this is referred to as a systematic error. Usually, both statistical and systematic errors are within a sensor's tolerance range. This is supplied with the characteristic sensor curve by the manufacturer and indicates to what extent the measurement results may differ from the true measurement. If a sensor's systematic error generates system responses that are no longer acceptable, the sensor must be replaced or the system concerned must be calibrated. This process involves the system's characteristic curve being changed. Calibration can be performed during vehicle production or later during a service. Some systems, such as the tire pressure monitoring system, can be calibrated by the driver himself. Other systems carry out calibrations automatically, as is the case, for example, with the clutch system on the automated manual transmission. This chapter deals with sensor failure and the related effects. You will learn how control modules can detect sensor faults and how the control modules can respond in the event of a sensor failure. The next section covers the options available for checking sensors in fault diagnosis. Finally, you will see the solution to the case study in Chapter 1, in which a faulty crankshaft position sensor resulted in a customer's vehicle not starting up. Sensor faults can have various effects. If the sensor fails completely, the control module can no longer detect one or more physical variables. Depending on the sensor and its task, a sensor fault may only slightly impair vehicle operability or, as in the case study in Chapter 1, may result in the vehicle not starting up. Incorrect measurements also indicate there is a fault. Let's have a look at the example of a faulty NTC resistor which is used as the coolant temperature sensor. The measuring range shown here for the coolant temperature measurement is between -60 degrees centigrade and +150 degrees centigrade. The fault causes the NTC resistor to have a different curve to the manufacturer's characteristic curve. According to this curve, the sensor should have a resistance value of around 2 kilo ohms at 30 degrees centigrade. However, the faulty sensor does not reach this resistance level until a temperature of around 78 degrees centigrade is reached. As this temperature is still within the sensor's normal measuring range, the control module cannot detect the fault and carries out its tasks based on false assumptions. This may result in, for example, incorrect system responses or incorrect displays in the instrument cluster. In this case, a cold start would not be implemented, even though one is required. Control modules are sometimes able to detect sensor failures based on the measurements that they output. Have a look again at the sample characteristic curve of an NTC resistor on the coolant temperature sensor. At minus 60 degrees centigrade, it has a resistance of around 550 kiloohms, and at 150 degrees centigrade, a resistance of 60 ohms. A resistance higher than 550 kiloohms will be detected by the control module as a break in the line, whilst a resistance lower than 60 ohms will be detected as a short circuit. Control modules can also detect sensor failures on the basis of plausibility. For example, the BAS release switch, the brake lamp switch, and the diaphragm travel sensor on the pneumatic brake booster must provide measurements that correspond with each other. If inconsistent information is recorded, the control module detects this and can respond accordingly. When a sensor failure occurs, a control module may respond in a variety of ways, depending on how the software is designed. Instead of using the measurement of the faulty sensor, for example, it may use a comparable measurement from another sensor. If the transmission fluid temperature sensor in the automatic transmission should fail, for example, the measurement from the coolant temperature sensor is used as a comparable variable instead. If the function of a faulty sensor cannot be replaced by another sensor, the control module uses a pre-specified or calculated default value instead of the measurement. An example of this is the coolant temperature sensor. If this fails, the control module assumes that the engine is cold when started, and when the engine has been running for a while, it assumes that it has reached the normal operating temperature. Both situations are programmed into the control module as a computer model and temporarily take over the function of the sensor until the sensor is replaced. The programmed default values thereby ensure the safety of the system, even in emergency running mode. There are, nevertheless, other situations where the control module switches off the affected system or even prevents the vehicle from being driven if no sensor signals are received. A vehicle's sensors can be checked once they have been installed. To do this, Star Diagnosis is connected to the vehicle's data link connector. The sensor's measurements pass through the associated control module and the onboard power supply to Star Diagnosis and appear in the actual value display of the Diagnosis Assistance System, DAS. To check whether a sensor is working correctly, however, it may also be useful to remove it from the system and place it in a defined environment. It's then possible to check whether the measurement result corresponds with the ambient conditions. For example, the coolant temperature sensor can be placed in a bath of water with a known temperature. A comparison of the measurements with the data from the manufacturer's characteristic curve will show whether the sensor is working correctly. With some sensors, it is possible to display the signal curve of sensor signals graphically using an oscilloscope. The result can then be compared with the corresponding correct pattern in star diagnosis. Using these correct patterns, a quick decision can be made as to whether a sensor is working correctly. The details of the curve do not need to be analyzed. The example shows the sensor signal of the faulty crankshaft position sensor from the case study in Chapter 1. Its signal form clearly differs from the correct pattern. Do you remember the exact circumstances of the case study in Chapter 1? The customer's vehicle cannot be started again after it's been standing outside overnight in cold weather. After it's been standing in the heated workshop for a few hours, the service employee manages to start the engine without any problems. The cause is an incorrectly installed crankshaft position sensor which is too far away from the flywheel. At normal starter speeds, the signal is detected. However, if this speed is reduced further because of the low ambient temperatures, as is assumed in our case study, it's possible that the signal will remain below the response threshold of the control module. The control module does not detect an engine speed and as a result does not put the ignition and injection systems into operation. The fault memory of the engine control module remains empty. As faults are not entered into the readable fault memory until they occur in a second drive cycle. In the heated workshop, the fault doesn't reoccur because the ambient temperature is higher. The starter speed is now higher. The sensor's signal oscillations reach the response threshold of the control module and the engine starts. The cause of the fault can be detected by comparing the signal form of the sensor with its correct pattern. This case study demonstrates that in certain situations, reading out the fault memory is not enough to detect a fault. In this case, it helps to know how the sensors function, their signal forms, and how the systems interact in order to find the cause of the fault. Let's summarize the main points again. When a sensor fails, the control module cannot detect a physical variable. The consequences of this range from slight impairment of vehicle operability to vehicle breakdown. Incorrect measurements also indicate there is a fault and can result in incorrect system responses or incorrect displays in the instrument cluster. Control modules can sometimes detect a sensor failure based on the measurements registered by the sensor. In other cases, a plausibility check is run. Here, the control module determines whether the measurements of various sensors correspond with each other. If a sensor fails, the control module may sometimes continue operating, using a measurement from another sensor as a comparable variable. If this is not possible, as is the case with some sensors, the control module relies on pre-specified default values, which temporarily take over the function of the sensor until it can be replaced. Sensors can be checked in a variety of ways. By displaying the actual values of the sensor in the DAS of star diagnosis while it is installed. By comparing the sensor signal with the correct pattern in the star diagnosis diagnostic tool. By removing the sensor and measuring it in a defined environment.